Welcome to our deep dive into the fascinating world of wave formation. If you've ever stood on a beach, mesmerized by the rhythmic dance of ocean waves, you're not alone. Waves aren't just a beautiful spectacle, they're a complex interplay of natural forces that shape our planet's coastlines and influence global weather patterns. Today, we'll uncover some lesser-known facts about how waves form and behave, delving into the science that turns simple wind into towering walls of water. From the gentle ripples caused by a light breeze to the monstrous rogue waves that have confounded sailors for centuries, each type of wave tells a story of energy transfer, resonance, and natural forces at work. By understanding these principles, we can appreciate the intricate choreography that governs the movement of water on our planet. So whether you're a seasoned oceanographer or simply someone who enjoys a day at the beach, this deep dive promises to offer new insights and a deeper appreciation for the waves that shape our world. Let's embark on this scientific adventure together and unveil the secrets behind one of nature's most captivating phenomena. When we think of waves, the first image that often comes to mind is that of wind blowing across the ocean's surface. Ocean waves primarily form from wind. As wind blows across the surface, it transfers energy to the water, creating tiny ripples. These ripples grow into larger waves as a result of a fascinating phenomenon known as resonance. Imagine pushing a child on a swing. If you push at just the right moment, the swings get higher and higher. Similarly, when the natural frequency of these ripples matches the energy frequency of the wind, the waves amplify. Enormous waves that travel across entire ocean basins. So, the next time you see waves crashing on the shore, remember that they are the result of a remarkable interplay of wind and water, amplified by the natural resonance that governs their formation. It's a testament to the power of nature and the intricate mechanisms that shape our world. Gravity plays a vital role in wave formation, acting as the unsung hero that keeps everything in balance. When a wave forms, gravity acts as a restoring force, pulling the elevated water back down. This gravitational pull gives waves their characteristic shape and motion. Without gravity, waves would simply dissipate and lose their form. Surface tension also plays a crucial role in the early stages of wave formation. It can help amplify disturbances, leading to larger waves. Gravity influences wave speed, determined by wavelength and water depth. In shallower water, waves slow down, becoming steeper and more pronounced. Gravity and surface tension create the mesmerizing patterns on the ocean's surface. As waves travel across the ocean, they encounter varying depths and underwater features that influence their direction and behavior. This process is known as wave refraction, and it plays a crucial role in shaping coastal landscapes and wave patterns. When waves move, a phenomenon that can dramatically alter their path. The shape of the seafloor, or bathymetry, is a key factor in wave refraction. Underwater ridges, valleys, and other features can cause waves to converge or diverge, leading to areas of increased wave height and energy. For example, when waves encounter a submerged ridge, they bend and focus their energy, creating larger and more powerful waves. Conversely, when waves move into a valley, they spread out and lose energy. This bending effect is not just limited to natural underwater features. Human-made structures like breakwaters and jetties can also influence wave refraction, providing protection for harbors and coastal areas. By understanding the principles of wave refraction, engineers can design structures that minimize coastal erosion and enhance the safety of maritime activities. Wave refraction and ocean topography reveal the hidden forces that shape our planet's coastlines. Waves don't travel as isolated forms. They move in groups known as wave trains. Each wave within a train has a specific amount of energy, and as one wave dissipates, it transfers its energy to the wave behind it. This energy-sharing system allows waves to travel vast distances across the ocean, maintaining their strength and coherence over time. The concept of wave trains is fascinating because it highlights the interconnectedness of waves and the way they interact with each other. When waves form a train, they create a rhythmic pattern that can be observed from great distances. This pattern is not just a visual spectacle, it also plays a crucial role in the distribution of wave energy across the ocean. One of the most remarkable aspects of wave trains is their ability to transport energy over long distances without significant loss. This is possible because the energy within a wave train is continually transferred from one wave to the next. Wave trains also help to explain some of the complex behaviors observed in ocean waves. By studying wave trains, scientists can better predict the behavior of waves and their impact on coastal environments. Wave trains illustrate the continuous transfer of energy within the ocean and provide insights into the complex interactions between waves. While most waves are formed by wind, some of the most powerful waves are generated by underwater earthquakes, volcanic eruptions, and landslides. These events displace large volumes of water, creating tsunamis. Tsunamis are caused by sudden movements of the Earth's crust, creating long wavelength waves that travel at jet speeds. Waves radiate outward from the epicenter, traveling up to 500 miles per hour. As they approach shallow waters, their height increases dramatically. This process, called wave shoaling, can create towering waves. The impact can be catastrophic, causing loss of life and property damage. Rogue waves have long been a subject of maritime lore and scientific curiosity. These rare, massive waves can reach heights of over 100 feet and appear seemingly out of nowhere, posing a significant threat to ships and offshore structures. Despite their rarity, rogue waves have been responsible for numerous maritime accidents. The formation of rogue waves is a complex and not fully understood phenomenon. One theory suggests they arise from constructive interference, where smaller waves combine to form a massive wave. Another theory proposes that rogue waves result from wave focusing due to ocean currents. The unpredictability of rogue waves makes them particularly dangerous. Despite their elusive nature, rogue waves have been documented through satellite imagery and direct observations. Continued research and monitoring are crucial to understanding and mitigating the risks of rogue waves. On a smaller scale, the formation and behavior of waves are influenced by surface tension rather than gravity. Surface tension is the force that acts on the surface of a liquid, causing it to behave like a stretched elastic sheet. When small vibrations or disturbances occur on the water's surface, surface tension acts to smooth out these disturbances, creating tiny waves known as capillary waves. Capillary waves are the smallest type of waves and are typically less than a few centimeters in wavelength. Despite their small size, they play a crucial role in the overall dynamics of the water surface. When wind blows across the water, it creates these tiny ripples, which then grow into larger waves through the process of resonance and energy transfer. Surface tension is also responsible for some unique wave patterns, such as the capillary gravity waves that form when both surface tension and gravity influence the wave's behavior. Understanding how surface tension influences wave behavior can improve weather prediction models, enhance the design of marine structures, and contribute to the study of fluid dynamics. Surface tension is a fundamental force that influences the behavior of small waves on the water's surface. When waves travel away from their source, they naturally separate by wavelength in a process called wave dispersion. This phenomenon occurs because waves with different wavelengths travel at different speeds. Longer wavelengths move faster, leaving shorter wavelengths behind. This separation creates a wave spectrum, which describes the distribution of wave energy across different wavelengths. Wave dispersion is a fundamental aspect of ocean wave dynamics and plays a crucial role in shaping the behavior of waves over time. As waves disperse, they form distinct patterns and groups, with longer waves leading the way and shorter waves following behind. The energy spectrum of waves is a key concept in understanding wave interactions and behavior. It describes how wave energy is distributed across different wavelengths and frequencies. By analyzing the energy spectrum, scientists can gain insights into the source of the waves, the conditions under which they were generated, and their potential impact on coastal areas. Wave dispersion also has practical applications in various fields, including navigation, coastal engineering, and climate science. Understanding wave dispersion can help improve the accuracy of wave forecasts, enhancing the safety of maritime activities. Wave dispersion and the energy spectrum illustrate the dynamic nature of wave behavior and provide valuable insights into the forces that shape our oceans. The Earth's rotation influences wave motion, particularly on a large scale in oceans. This effect, known as the Coriolis force, causes moving objects, including waves, to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis force adds a layer of complexity to the dynamics of ocean waves, impacting their direction and behavior on a global scale.